Good afternoon, everyone. Thank you for joining in third session. Our resource person, Dr. Ravi Kumar sir, has already joined, and now he's waiting for waiting for us to take the session. So hope all will join in the time. So before I hand over this session to Ravi Kumar sir, uh, I would like to give you a brief introduction about Dr. Ravi Kumar sir. Dr. N.M. Ravikumar sir is a associate professor in mechanical engineering department at National Institute of Technology, NIT Warangal. He obtained BTech degree in mechanical engineering from JNTU Kakinada in 2000, Master of Engineering in Computer Integrated Manufacturing from PSC College of Technology, Coimbatore in 2002. He did his PhD in mechanical engineering from Osmania University, Hyderabad in 2011. After that, he did his doctoral research in 3D printing at Milwaukee School of Engineering, USA in 2012. He has supervised more than 30 MTech projects and produced 5 PhDs and guiding 5 more PhD theses right now. He has published more than 70 research papers in national and international conferences and journals. He has filed 1 international patent and 2 Indian patents in the area of 3D printing. He is instrumental in setting up rapid prototyping laboratory at NIT Warangal. He started MTech program in additive manufacturing in collaboration with Central Manufacturing Technology Institute, CMTA Bangalore, first time in India of its kind. He has established a world-class metal 3D printing facility at NIT Warangal under TechWip3 grant. He has conducted more than 15 training programs across India and trained around 900 participants in the area of 3D printing. He received Young Engineer of the Year 2009 award from the government of Andhra Pradesh and the Institute of Engineers India. He has executed sponsored R&D projects worth of 1.24 crore rupees in the area of 3D printing. He is the life member of ISTE, IE, and RPSI societies. He visited countries like Australia, Sweden, Singapore, Finland, France, and USA. So we are so much privileged to have Sir with us, and Sir is to give sessions on 3D printing, and such a great honor and privilege that we have. So now I hand over this session to Dr. Ravi Kumar sir. Sir, please.
Yeah, good afternoon, Dr. Srinivas and the organizers of this event. Thank you for inviting me to give a lecture in an Atal program. So on the novel materials, and my talk will be on the additive manufacturing and the novel materials in additive manufacturing. So that is my talk for today. And this talk will be predominantly on the additive manufacturing. So starting from introduction to additive manufacturing to say the conventional versus additive manufacturing, what are all the advantages of additive manufacturing, and what is this additive manufacturing and various steps involved in this additive manufacturing, and the materials. Nowadays, you can see good number of materials has been added to this additive manufacturing community. So we'll see the materials that are available for the additive manufacturing processing and applications of this additive manufacturing in various sectors, right from the medical to aerospace to automobile, tooling, art, jewelry, fashion, food, education. So you have, say, a wide spread of this application of additive manufacturing. And fabrication challenges, though we have a lot of developments, but still we have challenges in fabricating this additive manufacturing processes. And finally, the future direction of this additive manufacturing technology. So this is what I have planned for maybe next 1.5 hours or so. So this is the content I'm going to deliver during this session. And where additive manufacturing is fitting, say just we need to say recollect the various industrial revolutions. So, which we know the first industrial revolution. So it was during 1780s to 1860s, with the word coined as a mechanization, where the mechanical production systems are being used, say replacing the human muscle power, and steam energy and the water energy was the source of energy during that time, the first industrial revolution. And coming to the second industrial revolution, that is between 1870s to 1960s, where assembly lines has been say introduced, and electric power was the source of energy, replacing the steam and the water with the electric power. So that is during the second industrial revolution. And coming to the third industrial revolution, where the computing, information technology, automation and electronics was what the say major technologies, that is during 1970s to 2010, that is during third industrial revolution. And coming to the present fourth industrial revolution, so you have an autonomous systems, so you have a cloud computing and system integration, simulation studies, and IoT, Internet of Things, and augmented reality, virtual reality, big data analysis, cyber security. So like that, you have say several say technologies. But what is going to be the manufacturing scenario under this industry 4.0? So under industry 4.0, so the undoubtedly the manufacturing is getting shaped into additive in nature. So that's what various studies are quoting, that the additive manufacturing systems will be able to produce, say, many worth of parts and the end products by 2030. A lot of projections, a lot of expectations on this technology. So under fourth industrial revolution, so additive manufacturing is going to be the key technology that is for the manufacturing is concerned. So we have say uh, yeah, then let us quickly see so in order to before starting the additive manufacturing technology, we'll quickly see the classification of manufacturing process. Of course, you come across the subtractive manufacturing process like a CNC technology, where we need to start with the bulk material, which is excess of the product that you are looking at, and use tools to process or to remove the material until unless you get the required size and shape. You keep on doing it. But the major concern in this subtractive nature of manufacturing system is a scrap, huge scrap you are anticipating. And further, if you increase the complexity of the product, even it may lead to increase in the cost of production. So where we have other concerns like sometimes which we need to design a jig or a fix fixture to hold the workpiece. So like that, several constraints. So if your design has been changed from a simple geometry to say something like a coffee cup, like this kind of a freeform surface where you have to consider several constraints once you change the design from a simple geometry to a complex geometry like this. Why? Because which we need to your CNC or a subtractive manufacturing system so has to concern about the cavity that is too deep here to machine. So the tools that we need to approach, the what kind of a tools that we need to, and you have an undercut here, so which it requires say minimum 3-axis control of the say system, and which we need to design a fixture to hold from the bottom. That is an additional burden, and you have a sharp internal feature here which cannot be machined without a tool radius. So like that, so which you your approach has started from the bulk to bulk material with the block of material to the required shape, then which we need to consider these constraints. But whether these constraints may not be an issue once you come to additive manufacturing route. So in additive, so irrespective of the complexity, you are adding the material rather than you are removing the material in case of a subtractive process. Then there won't be any problem with the scrap or the wastage here in additive manufacturing, and there is no tool at all here, and there is no need for a jig or a fixer to hold the workpiece. So you are starting from nothing to final part. So as for your demand or as for your requirement, you will be adding the material rather than you are removing the material. So then you may have other manufacturing say practice like a formative process, like you have a casting or a forging technology where we need to make a die or a mold of the shape which you are looking at, and you will be say confining, or you will be applying the force to this dice, and then you are confining to the shape of the part, which is in turn the shape of the die. So then in additive, even we need not worry about making a die or looking for a tools. Just we need only the digital design. So that is only thing which we required for an additive manufacturing technology, and we need not much worry about all these constraints. So normally you come with the say conventional manufacturing systems, and you may get doubt then what could be the cost of this production of the part through additive manufacturing. So if you try to say plot the curve between cost per part to the number of parts, so which we know that the conventional forming process, so where like we were say casting or a forging process, which if you increase the number of parts, so your cost will be reducing drastically. And similarly for the similar trend can be expected from the subtractive manufacturing process. But whereas you can get a different trend here for a additive manufacturing, even though if you increase the number of parts, but your cost per piece remains same or maybe slightly reduced. So so then one can understand this may not be the technology for the mass production, but the trend is not mass production nowadays under Industry 4.0. This is going to be the mass customization things. The customization is going to play a vital role in the new industrial revolution. And of course, the complexity is also increasing day by day in the products. Say, if you take a simple geometry like this, so it may not be the much difficulty for a conventional manufacturing systems, and the cost involved is also very less. But if you your design as say design change has been made and it is more complex than the traditional design. Why? Because why you want to change the design means to improve the functionality or to reduce the weight. So you have come out with some kind of say topology optimized or some lattice structure or some sort of bionic design you come out with, and which is obviously by geometry it is very complex. And then once the complexity has been improved, say 4x times or 5x times. So your cost also, say, exponentially increased in a reverse manner in a conventional manufacturing process. But whereas in additive manufacturing, you are going to get this complexity as a free of cost. So means whether you produce this a kind of a part, or whether you produce this kind of a part through additive manufacturing, so the cost almost remains same. There won't be much increase in the cost, even though you have say a 4x 5x times increase in the complexity, but the cost remains same. And of course, you may be much worrying about the number of parts. So the number of parts may be restricting to a dozen or a few dozens of parts, which you can get say a very good outcome about this technology. And then not only the complexity wise this technology is meant for, say, in continuation with our discussions, like you have the cost versus complexity graph, and where your complexity is 1x times, and your conventional manufacturing can produce at the very cheaper price. But at the moment your complexity has been increased to 4x or 5x times, so your cost in the conventional manufacturing system is also going, say, 4 times or 5 times exponentially. It has been increased, but you can get the advantage of additive manufacturing here. So irrespective of your complexity, whether it is a 1x or a 5x, but your cost remains same. So that is the beauty of this technology. Not only this cost advantage, even you can come out with say a new geometric shapes. Say for example, I think you may come across your say tool design applications, where we need to design a conformal channels, cooling channels in a conventional say mold or die making industry, like where for injection molding or die casting, which we need to say um, drill this kind of cooling channels. But whereas these cooling channels, if you use the conventional manufacturing systems to produce these cooling channels, and you have a say limitation of say confining these channels to the shape of the say you can drill only a straight cooling channels, rather than if you use an additive manufacturing technology, you can confine these cooling channels to the say shape of the product that you are looking at. So it will enable you to come out with a new or innovative say procedure to improve the performance of the system. Here the cycle time is getting reduced once you use a conformal cooling channel rather than a conventional cooling channel. Normally you do in a say a tool design applications through a conventional tool making practice, but whereas you have an opportunity here. So like that you can keep on talking about several benefits of this technology under these circumstances. And then what is an additive manufacturing is all about. So the additive manufacturing, it is not a new technology, but it is say um, uh, yeah, this is going to be the 30-year-old technology. Uh, Probably the former name was rapid prototyping, where it was restricted to a designer's tool, where he used to make the prototypes very quickly. That's what the technology confined to a design domain, rather than expanding it to the manufacturing domain. In the recent times, it has been, say, matured this technology from the prototyping domain to the manufacturing. That's what you have the term called additive manufacturing. So this additive manufacturing, so is the word coined and the given the definition by the ASTM F229210. So additive manufacturing is a new process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to the subtractive manufacturing methods. And as a common terminology, even this name, additive manufacturing, is synonymally used as 3D printing. So why? Because it is the extension of the two-dimensional printing, where you have the third dimension. So where 3D printing is nothing but the fabrication of objects through the deposition of material using a print shed nozzle or other printing technology. And you call this technology either you name this as a rapid prototyping, or name this as additive manufacturing, or name this as a 3D printing. But the essence remains same, like which we need to start our journey with the digital model. So that is either you generate through a CAD/CAM CAE system, like modeling it through a geometric modeling technique, or even you have a reverse engineering system or a digitizing system where you can say replicate the physical object into a digital or a virtual model. So that is also going to be the start point of this journey of additive manufacturing. Even it could be a medical domain, like where you have a CT or a MRI scan data. That is also going to be the start point of this technology, say where you can make any complex anatomical structures, so making that used as a surgical model or an implant or an say a prosthetic or a device or a template or so for that sort of surgical applications you may use this technology. So this is about the technology is all about. So in a single sentence, additive manufacturing is a technology which is going to say convert the digital models into physical objects directly without writing any code, or more automated in the workflow. So that is about the additive manufacturing. Then what are all the various steps that consists of your additive manufacturing? So we need to just be understood that we need to start with the digital data. Either you sourced from a CAD, or either you sourced from the reverse engineering data, or either you sourced from a medical data, or any source of data, but it should come in a digital format. Then say let it come to the digital format of your product that you are looking at. So you are going to fabricate a coffee cup, the same example which we are talking about. So from the beginning, so you have an application to sip a coffee. So that is your application. So for that, you can go to any CAD package and quickly you can model this coffee cup. Or if it is already available in somewhere, just you can take that data, the digital data. Or if it is already there physically, you scan it and get it digitized, and that also will be acting as an interface or the input data for your additive manufacturing system. So then that digital data should come out with a particular file format called STL. STL stands for stereolithography. So where your stereolithography is a file format of say a triangular faceted mesh geometry. So that can be understood by say any additive manufacturing system. And you have an interfacing software with this machine. You will get that interfacing software will say take up this STL file, and this file will be transferred to the machine through this software. And in this software, you create a machine setup. So that machine setup is nothing but the list of commands or the instructions to run the machine. So what are all the instructions? So basically, it's a layered manufacturing which we need to send our data in terms of layers. That's it. So then you generate a cross-sliced, cross-sectional data or the layers in the software by specifying your, say, process parameters, like say what is the layer thickness and what is the speed of the nozzle, if it is a extrusion-based system or if it is a laser system. So what is the laser power, or what is the say the scan speed of the laser, and so on and so forth. So just you specify those process parameters, set those process parameters, and it will automatically generate a machine setup or instructions to send it to the machine. So inside the machine, the physical realization of these cross-sectional data has been realized here layer by layer. So again, you have a different energy sources. So, and then how it is getting interacted with the material. So material aspects we'll talk about. So then based on your say interaction with the energy source to the material, so then it is getting processed and it is getting bonded. These say feedstock and the further the layers, and it is getting one layer upon other layer, and it's getting fused, and finally you are end up with the final part which has started from the first layer to the last layer. And once you complete all that layers and then you remove that part from the machine, you unload that part from the machine, and once you unload it, then it have a different post processing requirements. Means like we need to clean the part, and we need to remove the supports which it has been given for ease of fabrication, in terms of the supports that it should be removed. And sometimes you are not satisfied with the surface finish and the physical properties and the mechanical properties. You're not comfortable, or you're not up to the mark or the requirements that you are looking at. So then, of course, which you can subjecting to a post processing like a furnace treatment or infiltration, or short pinning. So you have several methods that it should enhance your the properties of your the components that from as built from the machine, and further it has been post processed. And once you have done that, all the post processing, but post processing methods are optional. Why? Because what is your application, and the application demands, or the what are all the required properties here. Just you want to sip a coffee, then you may not be much worrying about the other, say, properties, which it may be aircraft engine component, or it may be an automobile engine component. So it may be subjecting to tedious, say, mechanical loads, and then in that case, which we need to do accordingly your post processing methods, and then you try to match your required properties in that case. So anyway, so these are the steps. Any typical AM process that you come across, it should follow. But here and there, your the feedstock material and the energy source may be differing, and with that, anyway, you may have a different physics of the interaction of this material with your energy source may differ from one process to other process. So that we'll discuss further. So these are the steps involved in any typical AM system. And coming to the materials, so can any material can be processed. So, but when this technology was started 30 years back, so it was only restricted to the polymer printing. So that too, more or less, it was either a thermoplastic or a thermoset plastic, or it may be a say semi-crystalline, or it may be an amorphous polymers. But nowadays you have plenty of materials has been added to the additive manufacturing say data bank. So then what are all these AM materials? So of course, which we can write from the polymers, we can process, and we can process metals. So we can process alloys, metal alloys, you can process ceramics, you can process composites, various kinds of composites you can process. And apart from these four standard engineering materials, even you can process the functional materials. So you can process electronic, shape memory alloys, and so on and so forth. So any functional materials can be processed, and even not only functional materials, not only engineering materials, even it could be processed natural materials, biological materials like tissues, or it may be blood vessels. So that is about the organ printing. So you have a lot of developments are happening in this direction. And even you can see food printers also now coming up for, say, food printing is also another area where you can even print the food, or even construction industry. So, and so on and so forth. You can say come out with your own material, maybe natural material, or even it could be a functionally graded material, or even it could be any tailor-made material. But whether all these can be processed, so then we will discuss that further. So then what could be the form of your feedstock or the raw material form initially? So whether it can be brought it as a powder form, in a granulate form, or even it could be a filament form, so which is of a wire or a rod, or even it could be a kind of a sheet or a laminate form, or even it could be a liquid form. So these are the four broad say the initial form of the raw material which you come across for the additive manufacturing technology. And as for the ASTM ISO 5290015, so it has been classified, this technology has been classified into 7 major groups. So we'll discuss a bit on this in the upcoming slides. So you have the material and you have the design, and now you have the say energy or an energy source, and you have the machine to so to process your materials as for your design or as for your say virtual model or digital model that it has been derived from any one of these sources we have discussed previously. So coming to say, let us first talk about the polymers. So the polymers, say, first you talk about plastics. So thermoplastics, even thermosets can also be done. And thermoplastics coming here, like say, you have semi-crystalline, amorphous, and say, as we know that, so if you go from this application limited say materials to say low temperature rather than to the performance, high performance, if you go up, and bit costly also if you come from the say the bottom of this triangle to the apex of the triangle, where you have say applications maybe limited or temperature withstanding, maybe a less temperature. If you talk about semi-crystalline, under that you have PPP or PLA, polylactic acid, and you have under amorphous you have ABS, and you have PS, HIPS, and PVC. So where it can be used for a commodity kind of application, say of these materials. And if you come to engineering applications, like you have a better properties and better performance of these products. Why? Because you can go with the polyamide, or you can go with the polycarbonate, or you can go with PPE and TPU and other grades of polyamide and nylon kind of stuff, where you can go with for the engineering applications. And still, if you are looking for high performance and high temperature products, and even you can go with the PEEK or PEA in case of high performance applications. So, and then coming to the thermosets, so you have a plenty of epoxy resins to process your products. So, which it will be say acrylite based, epoxy based thermosets, which it can. So you have a different say glass transition temperatures even. So we will discuss that also, like which you have each category of these say a material class, but you have a certain constraints, like which we cannot process thermoset as well as so the thermoplastic on a single machine. So which we need to say. So that purely depends on say what sort of say what kind of energy source you are using, and the raw material form, and how it is behaving. Like you have a thermal bonding or a chemical bonding, which you are going to say use it here to process your material. So that depends, and you have to select a particular technology to suit your required material processing. So, and coming to metals, so you have say right from the stainless steel, you have a different grades. I have put only the commonly used metal and metal alloys, which is of commonly used grades, but you can even extend this list with other grades and other alloys also. Need not be restricted to this, but I mentioned only the I have listed out here very well known and say oftenly used materials, but even it could be nowadays you have an open architecture kind of say systems, which you can tailor made your own material, need not be restricted to a standard materials or standard composition or standard grades of materials. And you have stainless steel 316L, 310, 17.4 and you have a tool steel, marazing steel, and H13, A2, and aluminum alloy like ALSI 10 mg, 8 mg, 12 mg. You have plenty of grades that it can be processed. And titanium, say 6.5, 6.4, ELI, or you have several grades of titanium so that it could be processed. But only the difference here is what is the environment that is getting surrounded by your material that matters. As we know that titanium and aluminum is a more reactive materials, which you cannot anticipate the same the conduction property or the absorption of the laser power. Basically, you may be using a majorly the laser power or electron beam or a plasma, which you often use it, but it differs from your say reactive material to non-reactive materials. But definitely, so you may be surrounded by an inert environment, and so things like that. So then you have to take care about your contaminations and oxidations, and then other that issues we'll talk at the end. So we have say aluminum and aluminum alloys, titanium alloys, and cobalt chrome is also which you have frequently used for medical applications and other applications. Even say you have a tungsten based materials, which now it is very oftenly used material, though, which you can know about these say alloys, the super alloys, how difficult can it be processed through a conventional manufacturing systems. And of course, Inconel nickel-based alloy, Inconel 625, Inconel 718, which is very proven materials for additive manufacturing technology, and Hast alloy, of course, and precious materials like copper, gold, silver, and so on. So these are some of the commonly used metal and metal alloys, but you can tailor-made your say material for your additive manufacturing process. So, and then these are some of the ceramics, commonly used ceramics, zirconia with 3Y and 8Y zirconia oxide, and silicon nitrate, alumina, and you have alumina, say toughened zirconia, silica, hydroxyapatite, calcium phosphate for medical applications and other applications and quartrate. So you have several ceramics. You know the different challenges of this ceramic processing than metal processing. So definitely certain challenges which we know that ceramics are totally different behavior than the metal, and ferrous, non-ferrous, and the ceramics, you have a totally different in a ball game. So anyway, you can find in the recent times the ceramic printers also coming up, and then material options in the recent times it has been so adding, and then coming to the composites. So composites, you can go with the FRPs, and you can onyx, nylon, and you can go with the continuous fibers like carbon fiber, Kevlar, fiberglass, HSST fiberglass, and of course metal matrix composites. So you can say customize your say compositions in your composites. But only thing is, so we need to come out with certain standards that are laid. So your feedstock materials should bring to that. Say majority, if you're talking about FDM based system, that is extrusion based system, and you have a certain, say maybe it may be a 3 mm wire, or it may be a 1.75 mm wire. So we need to, and then how do you get, say fabricate these fibers, and then these feedstocks for the AM say machines. So that matters, and then which we need to come out with that kind of following that sort of standards, and then you prepare your own material to be additively fabricated. This is about the composites. And you may have other materials, like you can do like a wax, and you can do printing in wax, printing in sand, printing with glass, printing concrete, and printing in living cells, or the skin, or organ printing is on, like where you can even cultivate these cells by using cell cultivation, and further it can be grown in an incubator, and then you have excellent scope in by using this additive manufacturing technology to fabricate say even living cells or that sort, and even it can be a food, so can be any natural material which you can even uh, could able to print it through additive manufacturing process. And of course multi material objects like graded composition alloys can be so easily done through additive manufacturing through a DED system or through a powder bed system, so which is oftenly used for grading of these alloys. So and even you can make a metal matrix composites for your say titanium carbonate, and then which we can make these composites for your additively manufactured systems, which you can develop your material, and then you can say develop your material, and which it will say work on this kind of additive manufacturing technologies. But again, you may get doubts, sir. All the materials can be done on a single machine, but that may not be possible. So you have certain constraints that we are discuss soon. So then you talk about the polymer processing, polymer material processing through this additive manufacturing technology. So first, we are talking about the polymer. That is a single step, means direct part production. Say the type of material is a polymer. So the state of fusion either use a thermal bonding or a chemical reaction bonding. You have broadly two kinds of say fusion, either through a thermal bonding or a chemical reaction bonding. And then the material feedstock, say you bring it in a filament form, just now we have discussed, or the melted material. In case of say you have a different say how your feedstock is getting distributed, your material is getting distributed. So broadly, you have either a nozzle or a print head, or even it could be through say powder has been laid as a bed, or even it could be a sort of a liquid vat, or it could be a laminate. So if your say feedstock is a filament, and then you will be taking it and melting it, and through a thermal bonding it, so you are say extruding it from the nozzle. And the basic principle here is you're melting and say solidifying and getting, say you melt the polymer here in the form of filament, and that say melted semi-liquid form is coming from the nozzle, and it will be start depositing and getting fused one layer upon other layer. So that is the material extrusion process. So and then you have say a print heads, means something like your inkjet printer, how it jets the ink, and here your print head may be used here to jet the melted material. So then you have a multiple jets here to say even you can go with the different materials, multiple materials, and you can go with different composition. So where you can do a multiple material jetting, and then that process you call as a material jetting system. So you will be using a thermal bonding here to get the bonding between your say the jetted droplets. So which you will be either using a sort of say a laser, or even a kind of a light source. Why? Because these or maybe the photosensitive resins, which the polymer is a photosensitive polymer. So then it will be start exposing it simultaneously to the light, and which it will start solidifying, get it cured the liquid into a solid, and you will be controlling everything through your design, or through your the cross-sectional data that you already done in the software. So and you have even the powder material. You even go with spreading the powder onto the bed, and then you selectively you fuse the metal, the powder particles, this polymer powder particles. Just you will be sintering rather than so you will be selectively sintering the powder particles from the, say, bed of powder. So from the cake of your powder, then you will be selectively doing as for the cross section of your design. You will be doing that, and you will be finally getting your product. Or even you can jet the liquid through the print head. Say you may jet the binder here to say get the bonding between the powder particles here. Say in that case, you may be using a glue or a binder, the compatible binder with your material that you're using it. So then you can get the bonding through this binder or a glue that has been, say, jetted through that print head, and you're going to get the, that is called as a bind jetting process. And you may use a liquid material to jet from the print head, and say you may use the photopolymerization chemical reaction here it's getting. So either you done through the thermal bonding, or you done through the chemical reaction for the material jetting system, or even it could be a vat based system. Means you can take a tank, a liquid tank, and which you are exposing it to a light. So that is basically a powder chemistry, or the chemical reaction is taking place, and you're going to get your say curing action of that say component, and finally you're going to get your product through this is called as a vat based photopolymerization process. And you can take the sheet laminates by using chemical reaction, and then stack the sheets, and fusion of the stacking sheets. You do that process you call it a sheet lamination process. Like you have all the 7 processes can be employed for processing of the polymers in a single step. You're going to get it. So this is about the processing of the polymers. And then coming to the metals you can go in either in a single step or multiple step. Means furnace treatment, further it has been subjected, or if not, even you can even have an opportunity to start in a single step of your metal parts. So you have to type of material is a metallic material here. The state of fusion, either it's a melted state, or solid plus melted state, or solid state. So, and material feedstock, it is a filament or a wire kind of a material, or even it could be a powder material, or it is a sheet material, or a laminate or a sheet based material. And the material distribution, how you are going to distribute, and again use a nozzle for depositing your melted filament or a melted wire through the deposit through a nozzle. So and then you the basic principle here is you will be selectively depositing the material onto the substrate, and then further one layer upon other layer you will be doing it. And you have the energy source, either use an electron beam, laser, or inductive heating can be the laser is predominantly used energy source, or even you can go with other energy sources also. And you have the process called a directed energy deposition, where you can use an electron beam or a laser to process your melted state material, and then you will get that process, the direct energy deposition. And you may use inductive heating, that is in a material jetting process. And then coming to you have the powder material, and you create a bed of powder, and selectively you fuse the material in a powder bed. And again, you may use an electron beam or a laser will be the energy source. So that is called as a powder bed fusion. This is the metal parts directly you can produce it. And you have the solid state. It's something like a welding based process. Like you have the sheet material, sheet will be stacked, and you have a fusion of sheets, and then ultrasonic ultrasound say welding can be used here. Solid state welding, you have a sonotrode, so then you will be doing that bonding through this ultrasonic say energy here to get the bonding between your laminates or the sheets. So that is called the sheet lamination based technology. So this is a single step you can process through the or even you can go with a multi step metal EAM. So like you in that case you can start even the metallic say material or a ceramic material or a composite material, you can start your say the material, the feedstock material. So then the principle of adhesion, so either you go with a thermal bonding or a chemical reaction bonding. And the material feedstock is a composite material sheet that will be stacked, and you have the basic principle here is the fusion of stacked sheets, and this is sheet lamination process, and you are going to get a green part here, basically green part or a composite material part which is joined by your polymer addition. But further it should be done through secondary process, like you go with the furnace sintering or say infiltration, with or without infiltration, which it should be further subjecting to the secondary processing. Say you can even go with see thermal bonding. You have a thermoplastics can be done through as a particle powder, which you will be so mixing with your say coating that sort of particles, binder particles onto this metal, ceramic, and foundry sand, which it has been coated with some binder, and you are going to that powder has been spread, and then selectively you will be doing that thing, and so we need to say debind that, and we need to do the post processing. Why? Because you're going to get only the green part, and then you make it as a brown, and then further you do it in a sintering of a furnace treatment, and infiltration should be done further. And even it could be a liquid or printhead. Through a printhead it can be jetted through a binder jetting system, and again you're going to get only the green part, and further it has been processed in the secondary operation. And even it could be through a chemical reaction, bonding through a liquid powder or a liquid through a vat system like ceramic powder. Say basically this is a light reactive photopolymer which is mixed with the ceramic powder, then that. And even you can go with a kind of a ceramic processing also. You have a vat based system here. So further it should be done through debinding and followed by sintering to get 100% say dense part, even in the ceramic or even in the metallic part that you are looking at after doing this secondary operations. So this is the kind of processing of the metals in additive manufacturing. Yeah, and we'll focus on the application side. So the applications of this additive manufacturing. So then, so coming to the materials just we discussed, so those are well-known applications or say frequently used materials, which we have been talking about. But even it could be you can develop your own material for that matter, like so as for your application demands, like so which we can have several applications, like we'll talk about the various types of aim that the industry segments are looking for this additive manufacturing technology. So of course consumer products and consumer electronics is the industry where you know that a lot of customization is needed in the consumer electronics and the consumer products, and even which we need to do electronic embedding of these things, and where you need to have a production of these tools and manufacturing equipment. So then you can easily do, and which we can see a lot of revenue has been generated through this segment of consumer electronics and the consumer products. 370 million euros of revenue has been generated through this. This may be a bit older statistics, but now by this time it has been still improvement has been happening in the recent times. And automobile industry, again you may be looking some sort of say the engine components or structural components, or even through say special components for your automobile industry, or jigs or fixers, say which we need to tools can be made for your automobile industry, for or even cooling ducts for the components for your automobile industry, where people are say using this technology. And you have see this revenue through automobile industry in the million euros. And then next industry is the medical and dental, where we need to come with a lot of customization or a lot of personalized, say, solutions for the healthcare industry, where each person is a unique in his dimension and the form and is, say, anatomy, human anatomy, bones, or is, say, so all these are, say, unique for person to person, and where this technology is meant for customizing these needs for each and every person. That is going to be the driving force of this medical and dental industry. So where you can produce a customized dental bridges for patients, or dental copings, crowns, caps, invisible braces for, say, teeth aligners. All are customizable to as per the patient requirement. And you can even customize the prosthetics for implants, maybe head implant, maybe joints, finger joints, or maybe hip joint, or and anyway, we have a dedicated session on this medical thing. We have a lot of potential that should be tapped in the medical and dental applications of this additive manufacturing. And more or less, it's more complex design. Human anatomy is supposed to be the more complex design in the universe. So you have such so advantage of this additive manufacturing: complexity, customization, personalization. So, and tailor-mading materials. So that is quite interesting. That is more encouraging. So aspects of additive manufacturing, of course, that is in medical. And coming to the aerospace, which you may be looking for a lightweighted structures, more strength to weight ratio of the components. And not only that, you have to be much cautious about your payload or the weight reduction. Maybe underhood components, or maybe structural components, or maybe cabin components. So even you could be able to save 1 gram, reduce the 1 gram of weight. It will save a few gallons of fuel for the entire life cycle, the entire service of that, say, component in the aircraft, or in a aero industry. That then that's what, like, where you can people are looking for these solutions, additive manufacturing solutions from the aerospace industry. But you can find even reworking or refurbishing the burners for the turbines, or say, so you can do a reworking or refurbishing these costly component. Otherwise, we need to scrap out, or you go with the welding for refurbishing. But the major problem with the welding is to have a lot of HSA, that is a heat affected zone. But you have a localized, say, heating and localized, it may not disturb the entire microstructural properties. You can produce monolithic structures and so on, like, which you can have a lot of advantages once you come to the aerospace industry in particular. But you have a unique advantages of each and every industry application. And tools and molds, I already mentioned, like the conformal cooling channels is the biggest asset for tool design people, in order to reduce the cycle time of your say molds, and you can make patterns, or you can make sand molds, sand cores, for your sand casting applications, or your injection molding, die casting applications. You can even make a pattern, use it as a master pattern for replicating it, or you can directly make the mold inserts for your application, which you can directly make by making use of this additive manufacturing technology. So you can make it in several fold, either a pattern, or a mold, or a die insert, or a core, sand core. So you can make. And then you have other industries, like you have several industries like military applications, architectural, oil and gas, space industry, and more customized solution in case of jewelry applications. So where you can, this technology has been highly appreciated by the jewelry industry, whatnot. All the industries that you can have a very good scope by keeping all in your mind. Like each industry may be targeting a particular characteristic of the product that you're looking at, and definitely this will cater. This technology will cater those. So it will satisfy, or it will cater those requirements of from the different industries. And if you talk about the aviation industry, say this is one of the well-known case study from General Electric, that is GE. Then we need to talk about the unique capabilities of additive manufacturing, or as such the design for additive manufacturing. So means say the traditional design, maybe it was consists of say 20 parts, but with the generative design approach, so you can make it as a single part, and then you can make it as a single part, and you can fabricate in a single setup, in a single go. You can print this. So means the 20 parts has been replaced. You know the importance or the advantage of reducing the part count in an say product. So this is what where the not only the part count reduction, so it has also reduced 25% weight reduction. So as we know that is a boon for the aero industry to reduce the weight, that to 25% reduction with the conventional or traditional design. That's huge saving in terms of fuel, in terms of even. So if you see the material cost, so this may be made out of say superalloy, that is more costly, maybe aluminum, maybe titanium. So which or Inconel, it's a nickel based say alloy, superalloy, but that is very costly. If you could able to even say save the material, so that is quite interesting. And even not only that, even it has been improved 5 times the durability with the conventional say design. And you can find about 19 nozzles for a LEAP engine that the Airbus A321 has been used here by the General Electric, that they are producing it. So you can find this sort of application. Not only this, you can even make a combustion chamber, which so you may get doubt, sir, can it be certified? Yes, it has been already certified, and they have the project started in so 4-5 years ago, and they got now the certification by this time by the FAA certified additively manufactured components. So that are there inside your say the engine of your aero engines that producing by General Electric or Rolls-Royce or any company that sort, which they are looking for an additive manufacturing solutions. So not only the engine components, even it could be a structural components. So the structural components, again, the bionic design. So this magic is all about in the design, right? Say, I hope we can understand the conventional manufacturing methods. You have the difficulty in fabricating either the honeycomb structures or a bionic designs or a lattice structures. So of any sort of complex or organically designed, say, geometries, that is very tough to make conventionally. But that is very easy here. So means that is the driving force of this technology. So you are inspiring, your designer may be inspired by the bionic design, so which is so making more lightweighting in the structural say part of your aircraft. The structural components has been further so reducing the weight by incorporating the bionic design or bio-inspired designs or the lattice designs or the sort of nature-inspired designs rather than or more in organic designs, like where you can get all these benefits. And you have a 3D printing bionics, say printing of this component, and it's a 15% weight reduction to the this lattice structure has been designed and fabricated versus conventional manufacturing methods. So these are the and this is another case study from General Electric. So 1/3 of the engine parts from the GE catalyst engine So that is advanced turboprop engine. So can you imagine that 1/3 of the engine parts has been fabricated and it has been, say, flying in the recent times. This 2020, they got the certification in the last year, and it has been started in 2015. What are all the benefits that you're going to get out of this? So you have a simplicity in terms of supply chain logistics. Otherwise, if you go with the conventional methods, you used to have a huge a logistic or huge supply chain for the conventional manufacturing methods. Either you go with machining or go with the investment casting. So you have a lot of supply chain requirements here. But here, say you have very few or less or compressed logistics or a supply chain, and you have a assembly is more simplified. Even you are able to consolidating the parts, that you are able to reduce the or simplifying your traditional assemblies, and your maintenance is also simplified because of your part count has been reduced, and even the weight savings, around more than 100 lbs of weight has been saved in this project. That's what the GE is quoting. And then you have an improved fuel burning efficiency. The performance of the system is also been enhanced with the comparison with the traditional, say, designs, and 10% more power, like that, which we can say the people are quoting from the General Electric, saying that these are the things they are getting out of this additive manufacturing practice, integrating their say manufacturing of their catalyst engines that has been used in the aviation purpose. And even it can be a monolithic thrust chamber with an internal cooling structure. So you can make it, say, a solid part somewhere, some region, and you can make it, say, you have fuel injection chamber here, this the thrust chamber, and you have the lattice structures here where you can see, and all are done in a single go. So it is not done separately and assembled. No, this is a single setup. It has been made, and which we can see. You can make this kind of lattice structures, which improves the cooling performance, and not only that, it's a double benefit. It's lightweighting the components. So that is the another advantage where you're going to get it out of this, say, lattice-based designs, and further fabricating it through additive manufacturing. So this is done normally through the CNC machining by the Inconel 718 is the material. So, but that is a great challenge for a CNC. A lot of wastage in CNC. But can it be done? This sort of a lattice structures, can it be machined? So that is the big question mark that once you go with the conventional manufacturing techniques. So that is what where you can get all these added value to the product, and heat exchangers where you can have a bio-inspired and more efficient designs. Say it may be a miniaturized, say, heat exchangers, or bio-inspired, like a lung-inspired, say, heat exchangers, which has been made using additive manufacturing technology, and aluminum or a copper is the material. Now you are now able to print in copper. So you have a spiral designs, and which is of 0.5 mm wall thickness. That is quite interesting. So even you can go up to a 0.5 mm wall thickness, and then 30% say lighter than the traditional design, and 35% cost reduction. So these are the advantages. And in this case, like this one case study, they are quoting again 22% lighter and 55 mm smaller than the traditional manufacturing parts. So that has been, and more or less, you're going to enhancing the performance of the cooling performance of the heat exchanger. That is, so where because of the bio-inspired nature, and then the complexity is free of cost here. You're not adding any extra money towards this complex designs, but that is done through conventional manufacturing system. That is a major drawback of the conventional manufacturing systems as far as these circumstances are concerned. And coming to medical applications, you can make an implant. So these implants, why it is so popular through additively manufactured. So means again the logic is same. That is um, customization and personalization and biomimicry of these tissues or the say bones, which the as for the say the bone structure, the how much porous that a particular patient. So you can have such a freedom in designing these implants, which is biomimicking either a chest implant or either a spinal wedge or a spinal cage that has been used, or need not be these areas has been restricted. So even it could be replacement of any joint, anything where you can do it. That's what companies like Anatomics or Jimmers or Stryker, these are the globally well-known medical device manufacturers. So they are looking for additive manufacturing solutions. The reasons are these are the reasons. And then even you have some complex surgeries where we need to plan the surgery. Maybe a pediatric heart surgeon has to perform um, a surgery on a month's baby or a day's baby. So how complex it will become for a surgeon, a pediatric surgeon, to operate a day's baby or a month's baby. And then once you have a model which is say regenerated from the patient say anatomy, and it has been used for intraoperatively in the surgery or planning the surgery or rehearsal the surgery. And nowadays you have a lot of FDA approvals and clearances has been given by the regulators for giving the certifications of these models, software systems, or the materials for that reason. Or you have several certifications that people are giving in the recent times to additively manufactured models or the implants or the prosthetics or the devices or the templates, whatever you are going to use it for your surgical purpose. And you have an orthopedic cast. Again, it is a lightweighting is a major, say, a challenge for an orthopedic cast, and you can make it more lightweighted as you can. So through a lattice-based designs. So then further it has been fabricated through additive manufacturing process. And even it could be a drug delivery application for personalizing the medicine, that is the dosages of the pills has been customized, personalized. So as per the patient requirements, it has been given, used in a drug delivery, a personalized drug delivery system can also be used this technology. So these are some of the medical applications. We'll explore the development and other aspects in the next session, probably that is tomorrow's session. But and automobile applications, we can even make a series where turbo prop engines, or even if people are using for say designing the dashboards or customizing the wheel. Say you have another advantage of the material in terms of here is you can make a biodegradable material that is can be easily printable, so that can be used in more sustainable fashion. That is another added advantage of additively manufactured components. And even you can make, say, lightweighted, say, car body designs, or for the Formula One car thing. Now we can have composites can also be done here through the additive manufacturing, and which you can even make use of those structures, composite structures that can be done through additively fabricated, or even it could be a manifold exhaust or intake manifolds of an automobile, which it has been say predominantly used by the auto industry to say manufacture these kind of components. And coming to the tooling applications, like it may be investment casting applications, where even you can produce a master pattern out of this technology, and further it has been molded into the casting. So you'll get the final part. So you are either using a master pattern, or you can make directly the tooling, injection molding tool inserts that you can made through additively fabricated say inserts, die inserts. And you can even make these aluminum tool or wax investment casting patterns to produce your these components through one of the additive manufacturing processes. So that is through ultrasonic technology. And even you can produce your um, say conformal cooling channels inside which you can see this is a mold, the cooling core for the conformal cooling channel, so which has been produced through additively manufactured parts. And further it has been the part has been produced from this say mold. So this is the part, this is the door handle of an automobile. So like this, which we can make use of this technology in terms of a tool jigs or fixers for automobile industry for tooling applications. Or even it could be a PMMA pattern with a green wax sprues, and then further it has been metal casted, or even it could be directly printed the sand, the mold cores, sand cores, and the sand molds for the casting applications. It's a semi-finished casting, and you have the say the core, sand core, and further it has been finished with the casted and finished the impeller, and you have the wax pattern, and further it has been say done casting by making use this as a master pattern, and further it has been replicated. So the idea here is that the customization, again, the customization is driving force, and mass customization. That is quite interesting scenario of this application in jewelry industry. Um, and art and jewelry, again, you have a lot of customized designs of the necklace or the rings or any art and jewelry applications, where oftenly you are looking for a lot of personalization of these products. So then that can be easily done through your additively manufactured components. So either you make it as a master pattern, or directly you can make as a part. Why? Because you have a huge material additions in the recent times, which you can directly make, or you can go with the intermediate process of say casting, means making a pattern and then preparing a mold. So that can be also done. So you have even in India, the biggest users of this additive manufacturing is the jewelry industry, which we can see a lot of customization in terms of these rings or jewelry items. So even last wax casting can be integrated with your SLA. How say refined say features you are going to get out of this SLA. This is a mold, and then you have a last wax casting process to further integrate this technology. You're going to get very fast and low cost production through this jewelry application of AM. And then even you can, it is not surprising to, so your next shoe, maybe 3D printed shoe that you're going to say wear, maybe at least a shoe soles. So the reason here is like you can personalize your shoe sole as for your say pressure points, right? Say that may not be that much worry about a common person, but an athletic or an diabetic patient, which he needs a certain personalization of these shoe soles. So that can be easily done through this additive manufacturing technology. You can personalize, so you can have a TPU as a material which you can do, that is a thermoplastic polyurethane, that you can directly print these kind of a lattice-based structures for more comfortable and more uniform distribution of your pressure points. So that is as for your requirement. So as for the user's requirement, which it is getting personalized. So you can explore these innovative applications of this technology in several folds. So I may be presenting very few case studies or a few industries that, but you can even think and explore this innovative solutions for the innovative solutions in any industry that you are looking at. And maybe 3D printed dresses, like for then say fashion designers, like where he or she wants to have a biomimicked, say a crocodile or an elephant inspired design that the designer has been designed, and further it has been printed through additive manufacturing process. So even that is the case for the food printing, like where again customization is going to play a vital role. Say you can mix your flavors, chocolate, or you can mix your fruit flavor, or you can mix your say vanilla or any other flavors that you can customize the things, right? So that is the biggest advantage, where you can customize your food, maybe chocolate, maybe sugar candy, maybe sushi, or even it could be you can prepare your own diet sheet, and then you can customize your food, and just you can customize and you can start printing it, and then you can make use of that food for your say consumption. So that's what where you can have this technology is meant for that. And last but not the least, even for the education purpose. So you have a lot of scope to integrate your AM technology into your curriculum. So unfortunately, we are not exploiting much. But if you go to a European country or the US or somewhere else, so where the 3D printers, the DIY, mostly the DIY, that's a RepRap, thanks to the RepRap movement, where it has been reached to a common person. Why? Because you have open source softwares and open malwares and firmwares to say build your own 3D printer, so that may be costing you a few bucks of money, rather than buying a proprietary machine which is costing you a lot. But now still, how best you can make use of this technology to integrating your curriculum, and for that reason, like the CBSE, they have already took the initiations to start integrating this kind of courses in the +1 +2 itself, and even at the lower grades of the school chain. And even AICT is also giving a proper encouragement for the thrust areas, like additive manufacturing and 3D printing is one among, like robotics, and you have other CSE and allied thrust areas which you can come across. And coming to additive manufacturing in education, you can say make any complex say mechanisms, or need not be complex, even a routine concept that we need to teach, and you can have a chance of experiential learning, teaching learning through the additive manufacturing process. Just you can make a model and then you can demonstrate. Then how do you get models? These can it be done through right from the scratch? Need not. You can have a user communities of 3D printing, or you can have say repositories that you can download these digital designs, but just for the hobby sake or the education purpose, not for the business purpose. You do use this designs. So these digital designs can be downloaded from the various sources. Then it can be further say print them and making use for your curriculum purposes and for your teaching learning purposes. So a fifth or sixth grade student has been given one assignment, say explaining the concept. If you construct the houses near the banks of the river, so then the erosion kind of a thing, how it's getting affected by the construction industry. Just a simple idea and simple thought and simple assignment. So can it be realistically shown in a more effective manner by using this kind of additive manufacturing technology in education? Need not be an engineer, even it could be a medicine student for anatomy classes, or for DNA structures, for a chemist, for a different structures. Then there won't be any limit. Say making use of this technology even in the education sector. It may be a science student or engineering student or a medical student. So you can integrate this technology into your curriculum. And you have a small scale and large scale components that can be done through additively manufacturing. Like you can have the one side is like a micro stents, which you can see, this is a micro scales sized stents that has been produced through a 2-photon polymerization process. So that is a photo material has been used here, and metamaterials has been used here. So this is the one, say, extreme side of the structure, the size of the structure that can be additively fabricated. It's a very small structure as on date, and even it could be the largest size of the real size building that you can construct through contour crafting technology, which it has been maybe a disaster relief for time being right now, for maybe a quarantine booths for the pandemic times. Then the people has been used to any disaster management right now. It has been used, but it can be exploited for the regular commercial construction business also. That is the potentiality of this technology in construction industry also. So you can find several, say, integration of one technology to other technology, to the 3D printing technology or additive manufacturing technology, to with robotic technology. Can it be, say, integrated, and can it be, say, your robotics has been integrated to your printing technology, and where you can make structures of this arbitrary in size, which it can be done through, or even it could be an unmanned aerial vehicle, or a quadcopters can also be integrated for the printing technology to have a more, say, action in here to have sit done through. And we'll come to the last phase of the presentation, that is there any fabrication challenges that are there in additive manufacturing? Of course, there are fabrication challenges that are there in additive manufacturing. If you see the material perspective, but I'm not a material scientist, but say, as the user of this technology, and the stated literature, I will try to explain. So, what are all the fabrication challenges that currently the additive industry is facing? So, we have the process and quality monitoring systems in additive manufacturing. Why? Because now you are talking about Industry 4.0, and you are talking about artificial intelligence, machine learning, and deep learning. Say, then can it be make it your additive manufacturing system as be more smarter, but still it is at the very beginning stage. I can say without hesitation, I can say this technology is still further must be a more smarter technology than now. Then say your why you are not able to get the quality as for on par with the conventional manufacturing like CNC technology. So the reasons are several. So right from your feedstock material, right from the starting of your material, and the specifications and the quality and the way you say prepare this feedstocks, and the way you follow the standards, but very limited standards are available in this area. But the reasons which we need to say explore it, the one way is right from the feedstock preparation. You have to say closely monitor and closely do control on it. Otherwise, you maybe end up with a bad part, or you maybe end up with the failure of the fabrication. So, and then you may have the process environment control, like it's very sensitive materials. It may easily attacked by the moisture. It will be the airflow effect, or it may be oxidation, contamination. So it may lead to several cracks or several problems or defects in your part. The way you are building it, the way the process environment that you are using it. So then that is also say throwing some sort of inaccuracies or the challenges in order to reach or get the required quality. And of course, the machine parameters, maybe laser power, if it is a laser driven nozzle, monitoring temperature, the head speed, nozzle speed, or laser scan speed. So it may directly affect your quality. So which we need to optimize these as for your how best you can make use of these process parameters, in order to get the optimal, say, quality. And then which further it should be having a challenges like, can it be done monitoring in situ, means while fabricating, can it be take some melt pool, say, monitoring or melt pool control, or heat maps. Why? Because you have a huge temperature gradients, and you have a huge thermal cycles or there, in each layer, or at the interstitials, or one layer to other layer. You have a lot of challenges here. Then can it be monitored? Can use some sort of sensors to be monitored? And can it be automatically controlled by automatically varying the process parameters? Can it be possible to further improve the quality of the fabricated parts? And of course, dimensional accuracy, surface finish, and your measurement and the post processing methods, can it be further, say, increase your quality of the AM fabricated parts? And post processing material quality testing, NDT, and destructive testings for further. So how you can, say, integrate this kind of computer aided testing to your this thing, and then online inspections. And can it be further increasing the quality of the AM components? And you have material testings in AM, like you have a destructive, non-destructive, and testing of the starting material quality, say, like what is the powder flow, flowability, powder particle size, contaminations, are there anything, or moisture content is there, so in the material, say, that should be done through, or even in situ melt pool monitoring, just now we discussed, and heat mapping. So can it be in process monitoring of the processes via a light beam or a spectroscopy for the kind of characterization, the kind of testing and the inspection will be done online or in situ, and ultrasound and AD current. But anyway, you can use the conventional methods that you come across, maybe a kind of ultrasound or AD current, or X-ray or CT inspection, or penetrate dye testing, or process, say, compensated resonance testing, or fatigue tough and shear tensile testing, and destructive testings, or some non-destructive as well as destructive testing, and other testing methods also. The most important part is the melt pool monitoring system, and then how you are going to, say, control your melt pool. You have the metallurgical history, or you have the, say, the thermal cycle history, and then and there where you can it be, they automatically control your process parameters in order to maintain the melt pool size as a constant, and the parameters, or can it be automatically adjusted? So you have a lot of scope, or further it has been integrated and developed along with these AIM systems. And you can have, say, other challenges, say, right from the material, as we discussed, like the material type, powder size, powder purity, that is going to the biggest challenge of the material preparation of your AM parts. And of course, design challenges, like you have a geometry, and you have overhangs and support structures. How do you, and what is the minimum size of the future that you can get it out of the machine? And that will dictate your, say, redesigning your parts sometimes, or modifying as for the design. Additively manufactured components, means you have designed for additive manufacturing concept, like, say, can it be designed as for the additively manufactured components? And then why? Because you never talk about support structure, you never talk about the part orientation, or you never talk about the other aspects of these challenges. Normally, you never come across the conventional manufacturing process, then which we need to, say, consider, and then accordingly we need to optimize the designs. So then you need to even have the design aspects, which you need to have certain challenges, which you need to come across, and then say take it those challenges, opportunities, and then keep working on it. And layout, like what is a horizontal orientation, vertical orientation, object proximity, and chamber filling, and so on and so forth, and organizing your build with multiple components. And the process side, you have around 180 plus parameters to control your, say, if you take a typical powder bed system, so it may be around 180 plus parameters to control your, say, quality. So then how do you prepare or optimize your process parameter set? Why? Because each geometry is unique. You cannot generalize these optimized parameters, or even you can. It will vary from material to material, right? So the behavior or the interaction or the thermal conductivity or the solidification rates, and totally it's different from one material to other material. So then how do you say come out with the optimal set of parameters for here? And then and during the post processing also, you have we need to have a heat treatment or short peening, polishing. So then these are like, say, which ultimately which we need to take up all these challenges each and every stage, maybe during a pre-processing or building or post-processing. So then your object accuracy and the surface quality and the material properties that it's going to judge, or it's going to have, and then you have to have certain considerations. So your tension, the surface tension, that's going to dictate your, say, balling phenomena, or certain errors or the defects that you come across because of the different surface tension at the different regions. So, and then you have the curling and deformations and other issues, and the heat dissipations, and you have staircasing effect, anisotropy in Z direction, especially in the build direction. So then you have all these considerations, and volume contractions and micro melting. So, and then you have several implications also to have, as on date, you have several implications to work on all these challenges. Like it's a thing where we need to work on all these challenges to come out with the best possible quality with the more economical cost of production. So I have listed some of the common defects that you come across in additive manufacturing. So first one is the balling phenomena. So this balling phenomena, so because of the surface tension, the differential surface tensions at different regions. So then instead of say laying a bead, so it may create a balling, uh, 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 like it won't deposit in a continuous manner. So it may be you can find some balling action where that is because of the surface tension and different surface tensions. So then how do you tackle this? Means like which we need to optimize the process parameters. So it should not be much say high power lasers, or then what is optimum power of the laser, or what is the scanning speed, the laser scanning speed, the optimum level. It should not be too much high, or it should not be too much low. So then what kind of optimal set of these parameters? And you can find some keyholes because of this vapor bubbles that has been formed. It will create the key holes, and so on and so forth. Even the chemical degradation and the oxidation. So then you have the metals, say, so it will always chance to make an form an oxides. Say then how do you say do that? Say tackle that, maybe you go with the inerting, or so, and then chemical degradation, or the another cause, or your moisture, or that kind of things, where it may lead to having forming the oxides. So, and then you have sometimes the cracks will be formed because of at the one layer upon other layer, where you have certain say not done properly, the melting is not happened properly, and then it may lead to form a cracks. And then delamination, so you have one layer upon another layer, it's again it's not proper sintering or proper melting of these, then it may lead to a delamination problem. And of course, distortion, say shrinkage, warpage, and again polymers. You have a different thing, and the metals. So you have these problems, and some inclusions or poor surface finish, maybe state casing effect, but maybe because of the inclined surfaces or down facing surfaces, and the porosity is another drawback, which you may be several reasons, maybe there's a porosity, but you may say do certain post processing, hipping, or sort of furnace treatments to come out with a 100% dense part. But still, you need to go with the post processing method to come out with, or some extent you identify where you have these problems, and can it be say minimized, so during your processing of these materials. So, and then say what are all the standards that are available in the market, the ASTM or ISO. So though this technology is 30-year-old, but ISO or ASTM for additive standards has formed around 17, 18 years back, where they are started developing various standards. But as on date, around 35 to 40 standards has been developed and published, and around 35 to 40, another 35 to 40 has been under development at the various stages, various phases, like right from the design guidelines. You have a general design guidelines, or the powder bed design guidelines, or the DED system guidelines, or even functionally graded materials. You have a certain guidelines for the design, and you have a material exclusion design guidelines, and you have design guidelines for post processing. So you have, these are some of the design guidelines that are available. And coming to feedstock standards and the feedstock guidelines or the feedstock standards, so characterized powders, you have say titanium 64, you have F2924, and titanium 64, the ELI, you have 3001, and Inconel 718, Inconel 625, stainless steel 316, and then aluminum 10 mg. So you have certain say standards. And coming to the file formats like STL, as we are talking about, that is even a old file format, but still it is going as a de facto standard. But they are trying to replace that with an AMF file format with the new standards. And then the purchase of AM parts for also you have a standards from ASTM and ISO combined, and fabrication standards for the testing of the specimens and the evaluation of the mechanical properties of the metals, and you have the part properties for the cobalt chrome, and you have the thermal post processing standards, and this is for various powder bed systems and the DED systems. This is exclusive for metal printing area, and you have the titanium via powder bed or test artifacts, geometrical capabilities, or terminology related standards has been developed, it has been published. So this is, as on date, you can find the ASTM standards and ISO standards together. And then what could be the future of this technology? Though you have a 1 dimension, 2 dimension, 3 dimension, and now people are talking about and developing about the 4 dimension printing from the MIT, great MIT labs. They have started modeling and bit started experimenting with the 4 dimension printing. And is it going to be 5 dimensional printing? No, actually, that is a gasset made during this time. That is not a 5 dimension printing, but that is the 5 axis machined component, as a deposited component, rather than it's not a 5D printing. So, but what is the 3D printing is all about? As we know that you have the material and you have the printer, and ultimately you are going to produce a static structure. But if you come to the fourth dimension printing, so that is for the period of time, your say a static structure may be converting it into a more dynamic or more intelligent structure. So how it is getting converted? So of course the material is going to play a vital role here. So maybe a shape memory polymer or a hydrogels, or any smart materials that has been introduced here with as a material. And you have the multi-material 3D printers that are now existing, and it can be further developed in the future. And inverse problem modeling will be done for this material as for the multiple materials, and you're going to get initially the static structure, and you apply the stimula, like it may be a temperature, water, energy, or you apply the stimula to this static structure and do a mechanism of interaction, and then ultimately you're going to get your structure is more smart or more dynamic or more intelligent structure. So the example, like you have a 3D printed say part like this, and then over the period of time means the shape has been transformed. So that is because of the stimula that you have applied, maybe temperature, water, energy, any sort. So you were over the period of time, you were say the structure that has been statically printed initially, and it has been transformed. It has been say transformed into a more dynamic or more intelligent. When can you say it is intelligent? Means as for the situation, as for the requirement which it should transform. But how do you get control? That is the transformation control through the stimula. That is going to be the major challenge for this 4D printing. And then people are working that, and then you can find a lot of breakthroughs from the MIT in this direction. And even it could be a more intelligent towards screwing, unscrewing, gripping, gripper, or even it could be say what do you call? You have say even a life-saving application, like if you have a stent which has been done in your heart, and then whenever you have a massive stroke, can it be say automatically without blocking your blood circulation? So can it be acting as a more intelligent in that situation? So that is a life-saving application of the 4D printing application like that, which we can talk about several things. And then in the future, which you can see, you have more micro-sized components, or more self-healing microstructure components, or even you can make a batteries for your electric vehicles, or even it could be a combination of digital and analog structures. So that is, you can able to tailor made your materials. So that is quite interesting stuff. So it is a combination. The product is combination of more the static as well as a dynamic, or digital as well as analog composition of the product. So then what could be the future? Is it be going to be the layered manufacturing, or it's going to be the voxel based assembly? So you have then voxel assemblers where it could be, say, further assembled millions of voxels per second, and where it is getting done. So this is where we can expect the future direction. So let me summarize what I have done for the past 2 hours, almost touching 2 hours. So we have started with an importance of this additive manufacturing in Industry 4.0, and that is what where we have started, and compared the conventional versus additive manufacturing processes. And AM materials, we have discussed the commonly used materials and applications of AM in various fields like medical, aerospace, automobile, tooling, or jewelry, fashion, food, education, and fabrication challenges also discussed, and the future direction of AM. So this is what we have discussed for during this session. And coming to the facilities we have at NIT Warangal, we have a metal 3D printer which can capable of printing in metals. From 3D systems make the DMP flux machine, and couple of Stratasys make Dimension series and Mojo series machines, and desktop based printers like Ultimaker 2 Plus, AnyScan and SenseScan for these 3D sensors, 3D scanning devices, and muffle furnace and short pinning for the post processing of metal 3D printed parts. And we have a dedicated software for additive manufacturing. We have Mimic software for medical image processing, and we have Magic software for STL repairs and the tool design applications. And Thematic is for designing customized medical devices. And we have a Catalyst software, and we have a 3D Expert software for simulating these builds for metal as well as polymer systems. So these are these facilities we have at NIT Warangal. I hope I have done from my side. So if you're having questions, I am very happy to answer those questions, or any suggestions you want to uh, give on my lecture. So that is also most welcome. So you can say interact. Yeah. So it is over to you, sir. Professor Srinivas.
Yeah, thank you, sir. Thank you very much. Yeah, now it is the time for the participants. If anybody has any doubt or queries, you can please post through chat box, or you can directly ask, sir.
Yeah, please.
This session is very, very informative. And tomorrow also, sir is going to take another session and our FDP.